These experiments were carried out in collaboration with many colleagues. From various institutions across Europe and beyond. Now, some might wonder why anyone would study EMP, which may seem to be nothing more than unwanted noise. In fact, there are many various reasons why people study the laser-driven EMP. First of all, regardless of whether the EMP is artificial or natural, can lead to malfunction of electrical devices, including energetic infrastructure. Here I would like to remind the blackout caused by a geomagnetic storm in Quebec in 1989. Of course, all communication devices are very sensitive to the electromagnetic interference. I think this is a case which everybody of us knows very well. The noisy signals in the laser or else pulse power experiments. In worst case, the EMP causes not only the noise and signals, but can even damage the sensitive electronics. Such effects of function of electronic devices are particularly dangerous in the potential applications of lasers in biomedicine. And of course, regarding the inertial confinement fusion, thanks to the considered high laser energies, we should expect very strong EMP. I mentioned that I heard about an accident at Univ facility when the power supply was completely cut off due to strong EMP. Sometimes the EMP can be useful and promising for different applications as various technologies in defense, including both the jamming and destruction of electrical devices. EMC hardening, not only in aviation, but in all cases where high interference immunity is required. Another application is an emergency stopping of cars in the road transport, where instead of risky maneuvers or shooting, an EMP jammer can be used to force a driver or car to stop. And last but not least, you can find a number of articles presenting an application of electromagnetic pulses in biomedicine, for example, inactivation of bacterial cells, tumor therapy, etc. However, I think that the most interesting on laser-driven EMP is the EMP self, particularly physical mechanisms, its generation, which still have not been satisfactorily explained. Most likely, they are caused most likely not only by one mechanism, but there are many phenomena which, by their nature, must cause higher or lower electromagnetic radiation, like the time-changing magnetic fields within the plasma, the outer magnetic field driven by current of electrons, time-varying electric field caused by separation of charge by the escaped electrons. Of course, when the target is charged by the escaped electrons, this charge is compensated to the return current to the ground, to the target store, which generate time-varying magnetic field. This current would be in the order of kiloamps, so you can imagine what strength of this magnetic field could be. At this point, I should mention that an electrode dipole radiate not only on the frequency which is corresponding with its dimension, but it can radiate on any frequency actually, but with different impedance, so with different efficiency and with different directionality. But it still can radiate any electromagnetic wave with any frequency. The analysis of the electromagnetic pulses in the laser-driven EMP brings many difficulties, which are given by the nature of the experiments. You must be in vacuum. You must have an optics and many other devices in the vacuum chamber, both for the laser focusation and laser diagnostic, also for plasma diagnostic. So, in contrast to the ideal case for the EMP studies in anechoic chamber, the reality in our case is giving big challenges to us to understand what actually happened in the plasma and laser interaction. Some of these issues could be, of course, solved by simulation and modeling of the resonance and eigenfrequencies of the chamber and other hardware. Here, for example, is a paper of Fabrizio, which characterized the resonances of our experimental chamber at pulse, or you can use an analytical approach, considering the transversal and longitudinal standing waves within an amp, within the resonant chamber of square or different cross section. But you cannot never include all the device which is within the experimental chamber or in the laboratory, and all of these devices have their own eigenfrequencies and so on. So I would say that it's almost impossible to fully find all the frequency components of the EMP spectrum by the modeling of the eigenfrequencies of lab and the chamber. The experiments presented in this talk are carried out on pulse laser system, which is heptafluoride isopropyl iodine photodissociation gas laser, working on the photodissociation of this molecule, which I mentioned right now, which lead to photodissociation of the iodine, which stay in the excited state, convenient for the laser amplification. You can see the photo of the laser in this image. The laser has 6 amplifiers, or I mean 1 preamplifier and 5 power amplifiers, working on the wavelength of 1350 nanometers. The laser pulse length varies between 200 and 350 picoseconds. Maximum energy is up to 1 kilojoule, so the maximum power is around 3 terawatts, and the intensity of the laser beam on target with a faceplate, which gives us a focus with 100 micron diameter, is corresponding with 4 times 10 to 16 watts per centimeter square. Without the faceplate, now we are able to focus the laser into the 10 micron focus, so the intensity of the laser is from 10 to 18 to 10 to up to 10 to 19, which will be 1960. So for that. And the shot rate is 1 shot per 20 minutes. Here's the experimental setup, which is quite standard. So we have focus inclines inside the vacuum chamber. We have a faceplate, which we can easily remove to study both the interaction with faceplate or not faceplate laser. Within the vacuum chamber, we find B-dot and D-dot probes, several electromagnetic spectrometers to study the spatial distribution of the electron emission, and the target rotor is equipped by the target inductive current rod. Outside the chamber, you can find a couple of electromagnetic far field diagnostic, including the conical antenna for frequencies below 1 gigahertz, a pair of horn antennas for frequencies in the order from 1 to 20 gigahertz, and the T-dot probe, which is of the same construction and type as the T-dot probe inside the vacuum chamber. Now I would like to mention the new diagnostic which we have on pulse thanks to our colleague Univ, which made possible to focus the laser beam to significantly smaller focus than we had earlier, especially with the faceplate. So with the faceplate, so with the faceplate, the beam profile in the focus is you can see here in this image. So the diameter is of about 100 microns using the new diagnostic and new focusation mechanism. Without the faceplate, with faceplate we are not able to focus it so well. We reach a much smaller efficient area of the focus, which is close to 30 micrometers, where we should be 8,000. This is so. We reduce the focus efficient area so significantly, like you can see here. We also, of course, increase the temperature of electrons and the number of emitted electrons. So here you can see the spectrum of electrons, which was obtained in the experiments with this focus, with the faceplate, and with the diameter of focus of 100 microns, and the electron spectrum corresponding with the small focus, with the reduced focus, is here. So the electron temperature is approaching 1 mega electron volt. Now I will describe the diagnostic and result which we used in these experiments in the direction from the laser target interaction to the far field diagnostic. So we will begin with the target current probe. I think that many of us have heard about this probe. So this is in effect a small probe which is integrated to the target holder. And if the target is irradiated by the laser and electrons escape, the target is charged. This charge is compensated by the current flowing through this probe and the target holder to the ground. This current generates a time varying magnetic field which induces an electric voltage to this loop, and this voltage is proportional to the target current derivative. So the rough signal of this target current probe you can see here in this image. This is a target signal, target current signal from the shot without faceplate and with a energy almost 600 joules. We integrate to this ref signal. We obtain the current which is exceeding 10 kiloamps. Here you can see the scaling of the target current with respect to the laser energy, or more exactly laser power. And so on the left column, this is the rough signal. The right column is already the current after the integration. And first of all, you can see that there is proper scaling of the target current amplitude, and the energy for power from 0.3 terawatts to almost 2 terawatts. So this is something that we would expect, that increasing the energy, increase the amplitude of the current. What is more interesting, that at the shots with low energy, for example, 100 joules, the full Hilford maximum is of about half of nanoseconds, 520 picoseconds, for example. If we increase the energy 2.5 times more, the full Hilford maximum is reduced by 100 picoseconds. And if we again increase the energy by factor of 2 or maybe more, 2.5. We gain reduction of the current pulse by 100 picoseconds. So this is something what is I think it's new. It's presented in this paper, and the shortening of this target current pulse, of course, must be visible in the spectrum of the target current signal. So here you can see the spectrum. So this is the highest peak with a broader spectrum is corresponding with the energy between 500 and 600 joules. The intermediate energy around 400 joules, you can see here. And the lowest energies with 100 joules is the smallest peak here. What is very important that not only the bandwidth, I mean from 0 to 0, is increased, but also the center, I mean the top of this Gaussian-like pulse, which is also scaling with the laser power, as you can see here. So this top of the Gaussian-like distribution of the spectrum is shifting from 500 megahertz up to almost 2 gigahertz with the increasing of laser power. So these all results are obtained with the big focus, with the faceplate and the diameter of the focus with 100 microns. So now we tried also to scale not only with the laser power, but also with the intensity of the target. It should be more responsive for the electron emission, or more related with the electron emission and consequently with the target current. So here is an example shot with the faceplate with efficient area of 8,000 micrometers square and 550 joules. And the target current reached up to 4 kiloamps. This shot is with very similar efficient area, so we disfocused the focus, and we didn't use the faceplate. All the other conditions are the same. Very similar energy, very similar pulse duration, and practically the same or the same power. And the result is that the target current is practically the same. All the waveform is the same. We reduce the focus spot to efficient area 2050 micrometers square. We obtain target current pulse almost 8 kiloamps, so it's significantly increased by factor of 2. And if we minimize the focal spot to the 30 microns meaning vacuum, not on target, it's very important. We obtain current pulses which exceeds or reach at least 10 kiloamps. We try to make a scaling of the amplitude of the target current or with the laser pulse intensity, including the shots with various focal spots, and this is the result. We consider the 30 microns square, which we measure in vacuum, focal spot which we measure in vacuum. We should have higher intensities, which are represented by these green spots. But they are not fitting with these points with the smaller intensity and I mean with the larger focal spot. So this violet is for 2,500, those blue are for 700, 7,000, and the reds are for the faceplate shots. Okay, so the best fit we obtained, or more reasonable fit, I would say, if we don't consider 30 microns square focus by 500 micrometers square focus. This effect is most likely caused by the ablation of the material during the beginning of the laser pulse, because the laser pulse length is almost 300 picoseconds, and a few tens or maybe 100 picoseconds at the beginning of the laser pulse is very enough to expand the plasma, which then disfocus the very nice focus which we see in the laser far field diagnostic in vacuum. So this is the explanation, and this is also corresponding with the scaling laws that we corresponding to the laser temperature. We are rather behind or in the range between the 10 to 18 and 10 to 19 than at the higher intensities that are corresponding to the 330 micrometers square focus. So these results are from the inductive current flow. We would like to be 100% sure that that what we measure is really correct. So we try to measure the target current or target polarization by different independent methods. And we used a special high voltage pulsed high frequency voltage divider developed by Krzysztof Tomaszewski in Warsaw. And we couple the target to this voltage divider. This is the frequency response of this target voltage divider. And here you can see the waveforms which we registered on the output of this target divider. Again, we can see the nice scaling with the laser energy and power. And again, we can see the shortening of the of the current pulse with the laser energy or power. So this is the same effect. You can compare it with the selected pulses, exactly the same conditions measured by the inductive probe for 576 joules. So this is comparable with this pulse. And for the 95 and 97 joules, which are represented by the red curve here and blue curve here. But I would like to mention also that we do not observe only the shortening of the pulse, but also the appearing of this overshoot at the high energies. So this negative overshoot is both in the target voltage probe and the target current probe. Okay, and if we divide voltage by 50 ohms, which is the characteristic impedance of all the system, we obtain current, which if we have the same settings of the shot, in this case the base plate, for example here, like 500 and a half joule, we obtain practically the same current by dividing the frequency. And also, if we make, of course, there is a shortening, we made a fast Fourier transform of these signals, and again, we obtain the broadening of the bandwidth. We will move more far from the target. We place there a newly developed B-dot array to observe how the initial electromagnetic pulse change its shape with the distance, because with the increasing time and distance, more and more reflective waves and resonances should affect the pulse EMP which we measure. What we found that even after, let's say, 4 or 5 nanoseconds, the pulse which we detect is changed not so much actually. After the degradation, because this is exactly the same mechanism as in the case of the target current probe, we obtain the magnetic flux density, which is decreasing with the distance from the target. So you can see here. And its character is first very sharp Gaussian-like pulse, accompanied by some oscillation with the offset. To be 100% sure that we measure the voltage induced by the time-changing magnetic field, we try to turn the current probe by upside down, and we obtain exactly the same signal as before the rotating, flipping the target current probe, but with the opposite amplitude. So we can believe that the mechanism which induces the voltage is of the magnetic field origin, not for electric field origin or some, I don't know, hitting of charged particles, maybe, I don't know, effects of X-rays, and whatever you want. It must be by magnetic inductance, induction. We will go all far, the distance half a meter. We used B dot and B dot probes. I think that I don't need to introduce them longer. Here you can see sampler signal of the B dot, which was recorded with the oscilloscope with a sampling rate of 128 gigasamples per second. So this is the rough signal after integration and multiplication by the calibration coefficient or efficient area. We obtain the waveform of the time-changing magnetic field. And here you can see the FFT spectra from this signal. And again, as in the case of the target current, we can see the broadening of the spectrum with the increasing of the laser energy or power. Okay, of course, in this case, the broadening is more significant than in the case of the target current probe, because these probes are able to work much higher frequencies than the target current probe, where we expect that it's valid up to 3, maybe 4 gigahertz. I don't believe that it works higher frequencies. But in this case, yes. So after this first results, we wanted to be 100% sure that this is not some random effect of the configuration which we have. So we used completely different target and different target holder. So this is the spectrum for a copper bar with a cross section of 5 by 5 micrometers and the length of 5 by 5 millimeters and length of 50 millimeters. Then we used a copper foil with a thickness of 1 millimeter. It was a square form of copper with the edge 10 millimeters. Put it on a thin pin with a diameter of 1 millimeter. Of course, the shape of the spectrum is quite different because we affected the resonances within and around within the chamber and around the target, but still we observe the same effect. The spectrum is broadening with the laser energy. Okay, so to prove the reproducibility of this effect, we present an average of the magnitude from the FFT of these spectra from many shots sorted by the range of energies from 150 to 190 joules. So this is the red one. For the intermediate energies, blue one, and for maximum energies, the black curve here. So this is very reproducible. The same effect we observed in the signals of the D dot rod, which you can see here. Okay. If we will go to the greater distance, we find here a pair of horn antennas, which can measure to even higher frequencies than the D dot and B dot probes, up to 18 or maybe 20 gigahertz. This is the characteristic of these antennas. These two antennas, by the way, one Boden-Schwarz HF 906-7. This is the antenna from Institute of Plasma Physics in Prague, and also Fabrizio and his team bring to our common experiment their antenna of very similar type, also made by Boden-Schwarz. These antennas were coupled by special cables with extremely low losses devoted to the microwave applications. Before the experiments, we tested the capability of shielding and of our techniques to detect such frequencies during the shot. So this is spectrum from a shot with maximum energy without faceplate when these cables were unplugged from the antenna. So this is like reference. You can see that here is nothing. The signals were registered by the 33 gigahertz oscilloscope inside a Faraday cage. And this is the reference. So in the upper line, you can see spectra, FFT spectra from the signals of this horn antenna with vertical polarization. From the left to the right with increasing energy. So here is a shot with only 38 joules. You can see that most of the signal is below, let's say, 2 gigahertz. If we increase the energy, the low frequency part is slightly rounded to 4 gigahertz, let's say. And we begin to appear some signal behind 12 gigahertz, which is increasing with the increasing laser energy. So this is the wave play, and with the focal spot of radius 50 microns or diameter of 100 microns. And if we reduce the focal spot to the minimum which we are able to reach with a radius of 4 microns, and we begin with the lowest energy, so we are comparing these two signals, we can see that the highest frequencies are more significant than here. We increase the energy up to 160 joules. Again, we enlarge the amplitude of the 10 and 12 gigahertz components of the spectrum. And in the maximum intensity, which we are able to reach here, this component is even higher than the 10 and 12 gigahertz component, is even higher than the low frequency components, let's say, 5 or 4 gigahertz. We also tried to observe if this effect appears also in the case of a horizontally polarized antenna. So we use these two antennas, which are a very similar construction, to observe both the vertical and horizontal polarization in one shot. Okay. First, we set the antenna to the same polarization, and we made a cross-calibration shot. So you can see that in both signals, in both antennas, we can see these two significant components around 10 and 12 or maybe 13 gigahertz. Now, then we turn one antenna to have horizontally oriented electric field, and this is this signal, this is the horizontal polarization. And these components still you see. Maybe it's a bit reduced, but still it's possible to see. The explanation is not for that, but it is a fact. Okay, here we try to make a scaling of we wanted to somehow quantitatively compare these spectra. Not only to see it and we can see that, okay, it's larger, it's smaller, but we wanted to do it somehow exactly, somehow quantitatively. So we find the centroid frequency by the weighted average, and we plot it as a function of the laser pulse energy. Here you can see the red points with the faceplate and the black points without the faceplate, so the intensity is higher. At this point, I'd like to mention that all the points which are in this plot, they are obtained with the same settings of the experiment. The only what we changed is the pulse energy and the focus size. Everything else, like the target material, target coupling, target holder, target thickness is identical. Everything else is identical. This is the scale. So even if you change only the energy or the intensity of the laser, we shift the centroid frequency up to the frequencies exceeding 10 gigahertz. Similar scaling you can see in this right graphic, where we can see the difference between the shots with grounded target and insulated target. And what we can see that in contrast to the low frequency components up to, let's say, 2-3 gigahertz, where we can really observe that there occurs a reduction of the electromagnetic pulse by insulation of target. In the high frequencies, I don't see any significant difference. Now, in other case, we performed a comparative experiment at the Helix laser system at GSI in Darmstadt in collaboration with our colleagues from GSI. This laser system it's quite different. Of course, the principle of the laser is different. Wavelength is slightly different. So the pulse was 1,350 nanometers. There is a standard, the new 153 nanometers. We have longer pulse, but we have higher energies. We have smaller focus, what we will see very soon. If everything multiply and divide, we will obtain approximately by order of magnitude less than order of magnitude higher intensity of the laser on target at the Helix laser experiments. In these experiments, we used the same horn antenna from Institute of Plasma Physics in Prague. So this is the result here. This is the result from also from pulse from the antenna from the ENEA from Fabrizio, as we have seen. So this is what we will compare. This is the cable which we use. So in this experiment, we use the cable which I mentioned. This is the focus, which is smaller. This is the focus at Helix. The cable was worse, unfortunately, so we cannot compare it fully, like the ratio of the high frequency and low frequency components, because of these high frequencies, they have above 10 gigahertz, we have much higher attenuation on the cables which we use. But what is interesting, that regardless of the geometry of the vacuum chamber, of the experimental layout, and everything, it's very different, pulse and anesthetics. The spectrum detected by horn antennas in both cases have these components very close to 10 and 13 gigahertz. So we have two independent experiments with two different inputs, and actually three antennas, because this is antenna of Roden-Schwarz from IPP 907. This is antenna from Fabrizio 196. This is the same antenna. And this antenna is our homemade antenna with was developed and made at Czech Technical University. So if somebody would like to say that this is an issue of cable or issue of chamber or issue of antenna, I don't believe in that, because it cannot be in all experiments with different antennas, different cables, and different chambers. At the end of presentation, I would like to mention the very recent experiments on gas, laser-driven gas spark, where we used gas cavity the dimension 15 by 2, by 25, 150 millimeters by 25 millimeters. It was irradiated by 125 joules. So the advantage of this experiment, and what is interesting, is that there we can completely neglect or don't take into account a target current. What we observed? We observe EMP with the bandwidth up to 6 gigahertz, both with the near field probes, magnetic loop signing, and with the horn antenna. Now on conclusions. So the EMP spectrum is dependent on the laser beam intensity, both the shape and the bending. Target current pulse length seems to be dependent on the laser beam intensity. The target current measurement using the inductive probe and high voltage divider are consistent. The spectral centroid of the horn antenna signal scales well with the laser beam intensity. The unprecedented broad signals bandwidth significantly exceeding 10 gigahertz were observed in the horn antenna measurements. And the peaks around 10 and 13 gigahertz in the horn antenna spectra were observed in the experiments both at pulse in the ferric laser systems with different hardware and thus with different eigenfrequencies. EMP with bandwidth up to 6 gigahertz was observed in the gas spark experiment, in which target current is excluded. Thus, we must work on the theoretical explanation. We have some ideas, but we like to present it. Thank you very much for the attention.